Welcome S.Y.B.Sc students. In today's lecture, we study unijunction transistor, shortly called as UJT. A unijunction transistor is three-terminal switching device. Unijunction transistor consists of highly doped an N-type silicon bar with an electrical connection on each end. These connections are base B1, base B2 and emitter E. So this is first diagram shows UJT. This total is the silicon bar which is highly doped with N-type material, and this silicon bar has three terminals, base B1, base B2 and emitter E. Okay, and this is the symbol of UJT. Lower terminal B1, upper terminal B2, and this is the emitter which is on which arrow is pointed inward. Okay, the N-type bar is heavily doped with P-type material closer to base B2, which makes single PN junction. Okay, that means this N-type bar is heavily doped with P-type material which is closer to the base B2 and it forms PN junction. The lead of this junction is called the emitter E. Note that the emitter is shown closer to B2 than B1. The arrow on emitter lead points in the direction of conventional current when the device is in the conducting state. Since the device has one PN junction and three leads, it is commonly called unijunction transistor. Right? Since the N region is lightly doped, the resistance between the base terminal B1 and B2 is very high when emitter lead is open. Right? Then we see operation. So this is the unijunction transistor. First we see here is a no voltage is applied, right? Then this is a PN junction. Figure shows the basic circuit of a unijunction transistor. The UJT has normally B2 positive with respect to B1. So this B2 terminal, that base B2 is always positive with respect to base B1. That means base B1 is connected to the negative terminal of the battery. If voltage VBB is applied to B1 and B2 with emitter open, right, a potential gradient is formed along the bar from B2 to B1. Okay, that means when VBB is applied between B1 to B2, then potential gradient is formed along bar B2 to B1. Since emitter is nearer to B2, the potential between emitter and B2 is more than half of VBB. Right? The voltage between emitter and B1 establishes a reverse bias on the PN junction because the voltage between B1 and emitter is low. So it produces reverse bias on the PN junction. Due to this, the emitter current is cut off, but small leakage current flow from B2 to emitter due to minority carriers. Right? That means small leakage current flows from B2 to emitter, and this current is called as the leakage current, and it is due to the minority charge carriers. Now next we apply the voltage. Let a positive supply VE be applied to the emitter as shown in figure. So this positive supply VE is applied to the emitter. If input voltage VE is less than V1, the V1 voltage is here, that means voltage between center of this PN junction diode to the base B1 is called V1. If the input voltage VE to the emitter, if input voltage VE is less than V1, then the PN junction will remain reverse bias. If the input voltage VE to the emitter exceed V1, the PN junction becomes forward bias. As a result, holes are injected from P-type material into the N-type bar. These holes are repelled by positive B2 terminal and are attracted by negative B1 terminal. Okay. Due to this, there is a accumulation of holes in the emitter to base B1 region, which results in the decrease of resistance in this section of bar. So there is decrease of resistance between the section, that means between emitter and junction or base B1. Hence, internal voltage drop from emitter to base B1 is decreased and emitter current IE is increased. Due to increase in IE, more holes are injected and condition of saturation will be reached. The UJT is now in the on condition. If a negative pulse is applied to the emitter, then PN junction is again becomes reverse bias and emitter current is cut off. The UJT is then in the off state. Okay. Then we see equivalent circuit of UJT. This is the equivalent circuit of UJT. If you see the circuit diagram, then VE is the input voltage. This PN junction diode. This is the peak voltage, right? Then voltage between, that is junction, PN junction to the base B1 is V1. Then there are two resistors, RB2 and RB1, right? And this battery VBB is applied between base B2 and B1. The resistance between B2 and B1 of N-type silicon bar is called interbase resistance, RBB, right? That means this RB2 and RB1 is commonly called as RBB, that is interbase resistance. This resistance is represented by two series resistances, RB1 and RB2. Okay. Therefore, RBB equal to RB1 plus RB2. When voltage VBB is applied across B1 and B2, there is a flow of voltage across RBB. Here, emitter acts as a voltage divider tap. This emitter acts as a voltage divider tap. The voltage VBB is divided across RB1 and RB2. Therefore, voltage across RB1 is V1 equal to RB1 upon RB1 plus RB2 into VBB. Therefore, we write V1 upon VBB equal to RB1 upon RB1 plus RB2. Right? The ratio V1 upon VBB is denoted by eta. Therefore, eta equal to RB1 upon RB1 plus RB2. The voltage divider factor eta is known as intrinsic standoff ratio. The voltage across RB1 will be V1 equal to eta VBB. Okay. The value of eta is less than 1 and lies between 0.5 to 0.81. The voltage eta VBB across RB1 reverse biases the diode D. Therefore, the emitter current is 0. If a progressively rising positive voltage is applied to the emitter, then diode will become forward bias when input voltage VE becomes greater than V1 by Vd. The voltage Vd is forward voltage drop across the diode. Therefore, the voltage for which diode becomes forward bias when VE is Vp equal to V1 plus Vd. Right? This V1 you know, and Vd is the diode voltage, or Vp equal to, we substitute value of V1, that is eta VBB plus Vd, where Vp is called peak point voltage. The forward voltage drop across silicon diode is 0.7 volt. When diode becomes forward bias, holes are injected from P-type material to N-type bar. These holes sweep down toward the base B1, thereby decreasing the resistance RB1 between emitter and base B1. Hence, the voltage drop between emitter to base B1 is decreased. The emitter current now increases regeneratively until it is limited by the emitter power supply. Next we see characteristic of UJT. So this is the graph of potential emitter voltage VE versus current. Okay. When VBB is applied between B1 and B2 and emitter is open, then V1 equal to eta VBB is developed across RB1, which reverse biases PN junction. When input voltage VE is increased and becomes equal to Vp, then emitter junction becomes forward bias. This increases emitter current IE. So there is increase in emitter current like this. Due to flow of IE through RB1, the resistance reduces. Hence, when VE is increased beyond Vp, IE increases and RB1 as well as V1 decreases. The decrease in V1 causes more emitter current to flow, thereby further decreasing RB1 and V1. Figure show the curve between emitter voltage V and emitter current I. So along x-axis there is a emitter current and along y-axis there is a emitter voltage. So here is saturation region, this is valley point. This region shows the leakage current, this is the cutoff region, and here you see is a negative resistance region. Okay. Next point is UJT as a relaxation oscillator. In the circuit diagram of UJT as a relaxation oscillator, R1 and R2 are current limiting resistor. So here is R1 and R2 acts as a current limiting resistor. Resistor R and capacitor C determine the frequency of the oscillator. This resistance R and this capacitor C that determine the frequency of the oscillator. Now we see working. When power supply is switched on, the capacitor C start charging through resistor R. Okay, this capacitor C charge through the resistance R when this VCC is switched on. The charging of capacitor will continue till the voltage across it becomes equal to 0.7 volt plus eta VBB. Right? This voltage is the peak voltage Vp denoted in the curve that we have seen in the curve. After this point, the emitter to RB1 resistance drops suddenly and the capacitor start discharging through this path. When the capacitor is discharged to the valley point, voltage, the emitter to RB1 resistance climbs again and the capacitor start charging. This cycle is repeated and results in a sort of sawtooth waveform across the capacitor as shown in the figure. So this is the sawtooth type of waveform which is formed across the capacitor, right? So this is the time, this is the voltage. The frequency of sawtooth wave can be varied by changing the values of resistance R, because this controls the time constant RC of the capacitor charging circuit. To calculate frequency of sawtooth wave, assume that the capacitor is initially uncharged. Then the voltage across the capacitor Vc at an instant is given by Vc equal to VBB in bracket 1 minus e raised to minus t upon RC, where RC is the time constant. The discharge of capacitor occurs when the Vc is equal to peak point voltage Vp. So right here eta VBB equal to VBB in bracket 1 minus e raised to minus t upon RC, right? Therefore eta equal to VBB get cancelled in bracket 1 minus e raised to minus t upon RC. Therefore we write this e raised to minus t upon RC equal to 1 minus eta, or t upon RC equal to ln of 1 upon 1 minus eta, or t equal to RC ln of 1 upon 1 minus eta. Therefore frequency f is reciprocal of time period. Okay. So we write here f equal to 1 upon RC ln of in bracket 1 upon 1 minus eta, where eta is the intrinsic standoff ratio. Right. So with this lecture we stop here. Thanks.